Welcome back. New section, node voltage method in frequency domain. You see, in this chapter, we are only reinforcing the techniques that we learned in chapter 4. Node voltage method, Thevenin equivalent, source transformation, KCL, just about every technique we learned in chapter 4, we can use it in chapter 9, sinusoidal steady state analysis. Except that we are dealing with complex numbers. And I mentioned this in the past to you. Okay. So we are looking at some example problem for node voltage method. We are given a circuit that looks like this, and we are tasked and asked to find out the value of VG using node voltage method. How would we go about doing that? Okay. Let's first simply name all the nodes. Okay. Let's see if I can make it a bit thicker. So I'm going to call this node V1. Okay. And this node right here, I'm going to call this node V2. Okay. That's all I'm going to name. Okay. So we are applying node voltage method. In this case, let's start with for node V1. Okay. For node V1, you see KCL this node, apply KCL at this node, then the current coming in is negative 5 angle 0 degrees amperes plus the current leaving is via this branch and via this branch. Okay, so let's look at the current leaving in this branch first. Okay, so that will be this voltage V1 minus this voltage V2, so V1 minus V2 over the impedance there, negative J8 ohms. Similarly, what is the current flowing in this branch? Okay, it will be V1 minus the voltage here, which is given to be 20 angle 90 degrees by the impedance over here. So let me write it out. V1, which is this voltage, minus this voltage through that divided by that impedance. So V1 minus 20 angle 90 degrees divided by negative J 4 ohms. All of this equals 0. Okay, I can simplify this a little bit more. Okay, so we can simplify this a little bit more. We can factor out V1. If we factor out V1, you're going to see something like 1 over negative J8 ohms plus 1 over negative J4 ohms plus V2 times 1 over J8 ohms. All of that equals to 5 angle 0 degrees minus J20 by negative J4 ohms. Okay, you'll see that this is all equals to um, 0. Okay, all of this equals to 0. So you can find out the expression for um, this guy. Okay, so all of this is going to be 5 angle 0. This cancels actually um, to 0. Okay, all of this equals 0. So that is for node V1. At node V2, we can still write KCL over here. KCL over at the node V2. Okay, there is one current V2 minus V1 leaving. I can assume that current, and I can assume this current leaving as well. And I can assume this current leaving as well. So let's start with the current that's leaving towards the left, westward direction. Okay, so that will be V2 minus V1 by negative J8 ohms. Okay, so that's V2 minus V1 by negative J8 ohms. Okay, V2 minus V1 by negative J8 ohms. Okay, what is the current leaving in the bottom branch? Okay, V2, and if you assume this to be ground, V2 minus 0 by J8 ohms. So current leaving down is V2 by J4 ohms, isn't it? J4 ohms. That's the current leaving down. Okay, J4 ohms plus what is the current that's leaving in this branch? Okay, so we already accounted for all other branches. This is the only branch. That will be V2, which is this voltage, minus this voltage, which is given by 20 angle 90, divided by 12 ohms. So V2 minus 20 angle 90 degrees divided by 12 ohms. All of that should equal 0. That's by definition. Okay, so we can factor out V1 here. V1, we're going to fight it out a little bit more. Negative 1 by negative J8 ohms. So that is coming from here. Okay, plus I can factor out V2. I'm going to see negative J8 in the denominator. So that's negative 1 over J8 ohms. Then I'm going to see J4 ohms. So that's positive 1 over J4 ohms. Okay. Then I'm going to see this V2 over 12. Okay. So that's going to be plus 1 over 12 ohms. So this is 1 over 12 ohms, right? All of that equals J 20 over 12 ohms. Okay. It's going to be J 20 over 12 ohms. You think about it, 20 angle 90 is nothing but J12. Okay. Remember when you have an angle 90, that's J. When you have an angle 0, it's a purely real part. We looked at this when we looked at the rectangular form for 1, negative 1, J, negative J. Remember? So an angle 90 degrees is nothing but J. J 20 degrees by 12 ohms. Now, what else we got here? You see, we have two equations. Equation 1, all of this. So all of this is equation 1. We can simplify this, okay? Or we can simply throw it into MATLAB, okay? I'm going to call this equation 1, okay? Similarly, this guy is equation 2. If you write it in a format convenient for MATLAB, you'll get something similar to this, okay? You're going to see an equation that says V1 equals, if you throw it in MATLAB, you're going to get something like 2.6667 plus J 1.333 volts. Okay, That implies V1 is 2.981 angle 153.436 degrees. Okay, this squared plus this squared will give you this arctan of imaginary part over by real part. Make sure that your angle correctly depicts that the real part is negative. Okay, we discussed this in the example problems. Okay, similarly, V2 will come out to be, if you throw this in MATLAB, it's going to give you -8 plus J4 volts. Okay, which is the same as saying in polar form 8.944, okay, angle 153.436 degrees. Okay, now we should be able to calculate Vg, right? That is the original problem. What is the value of Vg? That is what we are interested in calculating. You see, you know V1 and you know V2. V1 minus this voltage, it's not V2, but the voltage at this node should give you a value for Vg, right? Vg is the voltage on the left minus voltage on the right. So voltage on the left is V1, which is so V1 is simply 2.981 angle 153.436 degrees, negative 20 angle 90 degrees. So it's better to change everything because we have a subtraction operation here. It's a good idea to change everything into rectangular form. So this becomes, okay, this becomes negative 2.6667 plus j 1.333. Okay, we know this already. We have seen V1 negative j20. Okay, so it should give you negative 2.6667 minus j 18.667, all of that in volts. Okay, so Vg therefore we're asked to find the time domain expression, which comes out to be negative 2.6667 plus or negative j 18.6667 volts. Okay, so that is the time domain, that is the rectangular form of the voltage Vg, which you have been asked to find out. All I did was to apply node voltage method. Vg is really voltage V1 minus the voltage at that node, which is shown by the 20 angle 90 degrees. Very good. Okay. All right. So that's it for this example.